Artificial intelligence is changing the way we work across all scientific fields. We use AI to analyze complex data, recognize patterns, make predictions, and help scientists to make decisions. But what happens when we bring AI into chemistry? Imagine you are a synthetic chemist and you have this target molecule to synthesize. This is a drug molecule named Sildenafil, also known as Viagra. So, you will start doing the retrosynthetic analysis of this molecule based on your chemistry knowledge and experience, and this might take several hours. But today, computational and AI assisted tool can help us to explore the possible synthetic routes much faster. Yes, in this video I'm going to show you how SciFinder uses AI and reaction predictions algorithm to assist chemists in retrosynthetic analysis. So let's start this video. So this is the SciFinder interface after login, and you can see that there are four icons. One of them is retrosynthetic analysis. Click over there. After clicking, you will see the chem draw will open. Here you can draw the structure of this sildenafil, but as you can see the structure is very big and it will take some time. Since this molecule is commercially available, so you can also draw the structure by entering the cache number, IUPAC name. So we can find the cache number by doing the Google search. So let's find the cache number. So this is the cache number. I will copy it, then go back to the SciFinder, paste here and click over there. Now you will see the structure of the molecule in a second, right? So it will save you a lot of time, but if it is not commercially available, then you have to draw it. Now let's start the retrosynthetic analysis of this molecule, and you will be surprised to see that this molecule can be synthesized only in one step. You can see that this is in progress. Okay, now the result is generated within a second, and this molecule can be prepared only in one step, and this is done experimentally. This is experimental step, and predicted step there is no predicted steps. So this molecule has been synthesized and there is a report, literature report, and there are three components of this reaction. So this is a multi-component reaction, and the interesting part, you can see the uh, price of each molecule of each starting material. If you click any one of them, you will see the supplier along with the price of the molecule with the quantity. And similarly you can click over other starting materials and you can order those molecules. If you don't want to uh, order these starting materials, or if you want to synthesize, then you can do further research. Okay, let's see this. There are three components, and this molecule uh, obtained in a 72% yield by using simple reaction condition triethylamine in dichloromethane in 2 hours at room temperature. Now if you want to see the synthesis of any one of the starting material, you can further click right click, and then there will be a pop-up window, this one, and you can see the synthesis of this molecule. There are 195 reports. So click over there and you will see the synthetic pathway for this molecule, pyrazole derivatives. As you can see that this is pyrazole derivatives can be prepared from the this ester to the amide. There are several other reports, but if you don't want to buy these pyrazole derivatives, you can further do the retrosynthetic analysis of this molecule also. So let's see uh, how many steps are involved to synthesize this ester. So there are six literature reports. Let's do the retrosynthetic analysis. As you can see, there is a also option for doing the retrosynthetic analysis of this molecule. So let's see what will be the result. Okay, so it is taking some time. Okay, now it's ready. As you can see that there are several steps to synthesize this pyrazole derivatives. It is not one step. So I think it is easy to buy this molecule, but if you are in a doing research in academic, then probably you need to prepare. So it is simple. You can use oxalic ester and ketone to make these pyrazole derivatives, and this is also experimentally reported yield. There is a predicted step also. So this one, as you can see, this green one, this is the predicted step for alkylation or esterification of this carboxylic group. What does it mean? It means this is not exactly reported. This step is not exactly reported, but there is a similar reports to convert the acid into the ester. So let's click over there on this conical flask icon, and you will see this methyl iodide reacted with potassium carbonate in the presence of potassium carbonate with this carboxylic acid, and you get the esterification. So that's why it is a predicted step. It is not performed exactly on the same molecule. Anyway, you will get the good yield. Its predicted steps are also reliable. If you click further, you can see that this pyrrolizole derivatives is synthesized in one step, and there are several other reports you can find. So as you can see that SciFinder generated a retrosynthetic analysis of relatively complex molecule like sildenafil within a seconds. As a chemist, we might spend significant amount of time thinking through different disconnections and possible synthetic pathways. But this tool can rapidly explore multiple possibilities and suggest you the potential routes. And it does not stop there. We can also explore supporting literatures, reported reactions, suppliers, pricing, and even perform further retrosynthetic analysis on the individual intermediates. But remember, the suggested routes still needs a chemist's judgment. We need to consider feasibility, selectivity, reaction conditions, cost, safety, and scalability. So AI is not replacing the synthetic chemist. It is helping us to explore the possibility much faster. The AI can suggest the routes, but the chemist still decides which routes make sense. If you would like me to test another molecule, leave it in the comment box.